Okay, in this last part of the video for chapter 5, turning effects of forces, we will be describing how does the position of the center of gravity of an object affects the stability of an object. So before we talk about how does it affect, let us take a look at what does it mean by the stability of an object. So the stability of an object is a measure of its ability to return back to its original position after it has been tilted by a small amount. So the stability of an object is being affected by the center of gravity in two different ways. Okay, firstly, by the position of the center of gravity, we say that the lower the center of gravity, the greater the stability of an object. And it is also affected by the base area of the object. The greater the base area, the greater the stability of an object. Okay, so let us take a look at this diagram. It can be found in your textbook. So I have a block over here. And then this block is uniform. So the center of gravity will be exactly at the center. So you can see these are dotted lines to determine where's the center of gravity. So the center of gravity is this black dot over here. It's a point where the entire weight of the object appears to act on. So the weight will be directly from the center of gravity vertically downwards. So this will be the weight. Okay, so these three blocks are the same. Okay, then I were to give a push to this block. Okay, I will tilt this block slightly about this point. So now my pivot becomes this point over here as my blocks tilt. Okay, so if the block is tilted slightly, okay, only slightly in this position, you will see that it is very stable because this block is able to return back to its original position if I were to release it. So this is what we call has a high stability because it returned back to its original position. So how do I explain it in terms of moments? Okay, there's always two parts that you need to explain in terms of the stability. So the first one, okay, you can see I've highlighted over here. Okay, it says that the vertical line through its center of gravity, it still falls within its base area. I hope you are able to see that the base area of the block is over here. Let me just highlight for you. This is the base area of the block. Okay, so this vertical line through the center of gravity or the line of action of the weight. Okay, I personally prefer the use of the line of action of the weight. So the weight is over here. So this particular line, okay, line of action is called the line of action of the weight, is still within the base area. So what does within the base area means? Means that now I will have a moment. So my pivot now is over here at this dot over here. I use the blue dot. Okay, so my pivot is over here. So this weight will actually create an anti-clockwise moments. Okay, so I move on. So the weight will create an anti-clockwise moment about the pivot. And this anti-clockwise moment will cause the block to rotate anti-clockwise. And so the block will return back to its original position. So the first step is always to identify whether this line of action of the weight is still within the base area. So if it's within the base area, you say that it's within the base area. If it's not within the base area, you say that it's not within the base area. So once it's within the base area, most likely it's very stable. It will return back to its original position. But why? It's because this weight will create a moment that bring it back to its original position. So now if I were to continue tilting this block, I tilt even more. I reach a point whereby now you take a look, the line of action of my weight is exactly at my pivot over here. So if my line of action of my weight is exactly at my pivot, we say that this block will be balanced over there because there will be no moments. So in this case, the center of gravity is in line with the pivot. There is no moments. It will stay balanced over there. Okay, then if I were to continue tilting even more, so if I continue to tilt even more, okay, my box will be like that. So now again, the first step, I need to talk about the line of action of the weight. So my base area still remains as here. Okay, my original base area of my block. Okay, and my pivot still remains at here. But now, the first thing I need to state, my line of action of my weight is now outside of the base area. My base area is originally here. So now once the line of action of the weight falls outside the base area, we say that the object is unstable. Unstable because it will topple if I were to release it. This whole block will topple. It will not go back to its original position. But why does it topple? Then I need to talk about my second bullet point, because now there will be a moment again, and now the moment is clockwise. So now it will create a moment that will cause the block to topple clockwise. Okay, so let's take a look at this one, which is present in your notes. It's more detailed. So let's take a look at point A. Point A, my block is not tilted. So the line of action of the weight, okay, you can see this highlighted one are the important points. The line of action of the weight is still within the base area. So nothing is going to happen. This object is in the original position, very stable. I tilt this object slightly. I go to position B. Again, position B, I need to state now my line of action of weight still falls within the base area. The base area is the red color highlighted one. Okay, so it's still within the base area. Then, so what? Means immediately in your head, if it falls within the base area, it must be stable. So how do I explain it's stable? You need to move on to my second bullet point, which is, so now I have a moment. My weight will create an anti-clockwise moment about point B, causing it to go back anti-clockwise. Okay, causing this block to rotate anti-clockwise and go back to its original position. So it's stable. At point C, the line of action of the weight is exactly at the pivot. So now there is no perpendicular distance between the weight and the pivot. So there's no moments, and this block will not turn at all. It will be balanced there, but it's just about to topple already. If I tilt even more, then now again, the line of action of the weight falls outside of the base area. It's no longer in this red highlighted area. It's outside of the base area. Then now the weight will create a clockwise moment, and it will cause the block P to topple. Okay, next. You may scan the QR code at the top. It leads you to GeoGebra simulations. You can play with it, but before you play with it, I want you to predict what happens to the initial tilt angle that is required to cause a block to topple when I increase the height of the object and when I increase the width of the object. At any one point, you can only increase one item, and you see how much that the block can be tilted before it topples. Okay, so this one, the first step, you predict. After that, you observe by playing with the simulation, by varying the height and the width. And then after that, you try to give me an explanation of why does the angle of tilt increase or decrease with an increase in height and an increase in the width. Okay, then you may scan the following QR code at the bottom. It will lead you to a Padlet page where you can tell me the answers. But I will not be doing this in the video. I will just go directly into the theory. Okay, so let's take a look. I have block A and block B. Okay, they have exactly the same base area. Okay, the only thing that I'm going to vary is the height of block A and block B. So block A has a high height. So the first thing you should recognize is if block A has a high height, the center of gravity will also be higher. Center of gravity will be higher because the center of gravity is exactly at the center of the block. So if I have a higher block, I will have higher center of gravity. Block B will have a lower center of gravity. So if I were to tilt them, okay, let's say I were to tilt them at an angle of 40 degrees each, you will see that for block A, which is the higher block, the center of gravity, because the center of gravity is higher, it would have already fallen out of the base area. Let me highlight for you where is the base area. Base area is here. Okay, and then in this case, so block A, it has already fallen out of the base area. Okay, but for block B, the base area is here. Okay, so the same base area for block B, the center of gravity will still be within the base area because the center of gravity is lower. So block A will be unstable because now there will be a resultant clockwise moment that cause this block to eventually rotate clockwise, so it will topple. And block B, there's a resultant anti-clockwise moment that cause this block B to drop back to its original position. So block A will topple first because it has a higher center of gravity. So the lower the center of gravity, the better the object stability is. Okay, that means I need to tilt over a very large angle before I'll topple over. So it means that it's very stable. Next one, let's take a look at these two stools. Okay, it has the same height. So the center of gravity is at the same height, but the base area is different. So I have stool Y that has a larger base area than stool Z. So again, I'm going to tilt it at an angle, and you will see that at 30 degrees, I'm going to highlight again. This is my base area. This is my base area. At 30 degrees, the one with a bigger base area, because the area is bigger, the center of gravity will still be within the base area. This is the point where it's just about to topple. Okay, so it will be balanced there. But for stool Z, okay, if I tilt it at 30 degrees, you will see that now the line of action of the weight is outside of the base area. So it is unstable. Why? Because there will now be a resultant clockwise moment caused by the weight. Okay, the weight is now to the side of the pivot, so it will have a clockwise moment. This stool Z will topple. So stool Z will topple first because it has a smaller base area. So in order to be stable, I need to have a big base area. Okay, so in general, to increase the stability of an object, we try to lower the center of gravity as much as possible. How do we lower it? We can add some weight to the bottom of an object. So once we add weight to the bottom of the object, the center of gravity of the object will decrease, or we just lower the height of the object. Okay, or we can increase the base area. We make the base area as big as possible, as wide as possible. Okay, so this explains why for your racing car. Okay, let me hide this first. Your racing car is very low, so it has a very low center of gravity, and then the wheels are usually at the side to increase the base area. So for your racing car, it has a very high stability to prevent it from flipping when it's turning at high speed along the bands. Okay, the same for this. Okay, you have a champagne glass and a normal glass. Okay, your champagne glass is more unstable because why? The height is higher. The center of gravity of your champagne glass is higher. So your center of gravity will be somewhere here. Okay, as compared to a regular glass, whereby the center of gravity is lower. So this one, higher center of gravity, it will be more unstable. Okay, it's also the reason why, for example, when you're taking an MRT or a bus, okay, and you have no handles to hold, you are standing up, usually we'll spread our legs wide. Okay, or even better if we can bend down a little. Okay, when we spread our legs wide, we are increasing our base area. And when we bend down a little bit lower, or when we sit down, that's even the best. When we sit down, our center of gravity is lowered. So the lower the center of gravity and the wider the base area, the more stable we are to prevent us from falling in the bus or in the MRT. So you may pause the video to think about the answer to this question. I'm going to go through now. Which of the following arrangement of books in a bookshelf will result in the most stable configuration? The answer here will be B. Okay, because in B, all the books are at the bottom, so the center of gravity will be lowered. Okay, all of them will have the same base area because all of them is the same bookshelf. But because B, the books are arranged in this way, I will lower down the center of gravity. There's more mass at the bottom of the bookshelf. Okay, next one. This is a thinking question. Why are passengers not allowed to stand on the upper deck of a double-decker bus? So you take a double-decker bus, you will see that at the upper deck, there can only be sitting passengers. There can be no standing passengers on the upper deck. Okay, this is for safety reasons. Okay, what happens if the bottom deck of the bus is empty and I have a lot of people at the upper deck? It becomes dangerous because if I have a lot of people at the upper deck, then my center of gravity of my bus would be higher, much higher. And when my center of gravity becomes higher, my bus becomes unstable. My bus might topple when it turns. Okay, it's also the reason when you take a tour bus, all the luggage are always loaded at the bottom of the bus. You don't have a bus that loads the luggage at the top of the bus. Okay, next one. Let's talk about balancing toy. Okay, so over here you have a comic strips that talks about balancing toy. He say, wow, how can that toy balance on the tip like this? So this is a dragonfly that can balance on the tip like this. Then this guy over here say, I think its wing distributes its weight and help it to balance. Then this girl say, no, I think the toy can balance because of its long tail. Okay, let's take a look at how does balancing toy works. Okay, so for balancing toy, the working principle is that its center of gravity is always in line with the pivot. So there will always be no moments because once the center of gravity is in line with the pivot, the weight doesn't create any moments. There is no perpendicular distance between the weight and the pivot. So no moments, no turning effect. So this toy will be balanced. The toy will not be toppled. So let's take a look at, there is two different types of balancing toy. Let's take a look at the first type. The first type of balancing toy is when the center of gravity is directly below the pivot. So how does the center of gravity is directly below the pivot of this balancing toy? So this type of balancing toy, usually they have heavy weights at two ends, and the heavy weights are usually at the bottom. So you can see that in this balancing toy, the two weights are sliding down over here, and then the tip of the balance is slightly higher than these two balls over here. So these two balls will cause the center of gravity of this whole toy to be downwards. Remember, the center of gravity might not be on the object. So in this case, the center of gravity is directly below this point over here. So this is the balancing toy. This black line with this pivot thing over here is the balancing toy. So the center of gravity is directly below it. Okay, so what happens when you put it on a stand over here? It balances. Okay, because there's no moments. The weight is here, the pivot is here, there is no perpendicular distance. So again, you need to mention why is it stable. You need to mention again the line of action of the weight is exactly at the pivot. So there's no perpendicular distance, no moments. This toy will remain stationary there. What happens if I tilt the toy? Okay, so if I tilt the toy to the right, this is what is going to happen. The center of gravity will shift to the left. Okay, so again, now at this point, you need to mention again, now the line of action of the weight, okay, is to the left, or the CG is to the left. Okay, you need to mention that the CG shifted to the left of the pivot. And now what will happen is it will create a anti-clockwise movement. Okay, anti-clockwise movement that cause the toy to rotate anti-clockwise until it goes back to its stable original position. Okay, so you can read the line of action of the weight is to the left. So now I have anti-clockwise movements, and these restoring movements will cause the toy to rotate and come back to rest such that the center of gravity will again be directly below the pivot. And if I tilt it in the other way, it will be exactly opposite. So now my CG is to my right side. I will create a clockwise movements, and again the toy will rotate clockwise until the CG falls below the pivot again. So this explains about the irregular lamina that we use to find the center of gravity. Okay, so the center of gravity will always lies below the pivot because at this point, this is the only point where there is no moment and this card will not move. If I were to rotate this card, okay, I cannot have the CG at this point because if I have the CG at this point, then I will have a perpendicular distance to my pivot and I will rotate anti-clockwise. So this card will rotate all the way until my CG is exactly at the center. If my CG is to the right side, okay, then I have my weight over here, and this weight will create a clockwise movement again. And this card will again rotate all the way until my CG is directly below my pivot. So that is why how I determine the center of gravity for irregular objects, it must always be directly below my pivot. So this is one type of balancing toy. Okay, then let me show you a video to illustrate what does it means. No. Okay, so these two balls are heavy, that lowers the center of gravity. This is my pivot, the one we are balanced about. No matter how you turn and flip, it will always balance because it will always turn until the center of gravity is directly below this foot. This is another example. So these two are very heavy objects. Okay, so these two objects will lower the center of gravity to a point directly below this pivot. So this will be my center of gravity. This is the pivot, the point where I balance it out. Okay, so if you see it's tilted like that, so my center of gravity will shift and shift to the right. Okay, so I will always rotate until my center of gravity is directly below the pivot. Okay, let's go into the next type of balancing toy. The second type of balancing toy, the center of gravity is above the pivot. But just take note that for all balancing toy, the center of gravity will always be in line with the pivot. It can be below the pivot, it can be above the pivot, but it is always in line with the pivot because only when it is in line with the pivot, there will be no moments caused by the weight, and therefore it will be balanced. So you see this is a roly-poly. In a roly-poly, usually the bottom part is very heavy. Why do I need it to be very heavy at the bottom part? Is to lower the center of gravity. I want to make this roly-poly as stable as possible so that no matter how I roll it, it will go back to its original position. So over here, you can see this blue color part is a very heavy object, very heavy mass. So my center of gravity is not exactly at the center of the roly-poly. It will be further down, much down. Okay, so next, so at this point where the roly-poly is standing upright, okay, you have your center of gravity directly above the pivot. So there is no perpendicular distance between the line of action of the weight and the pivot. So there will be no moment. There will be no moment, so it will be balanced like this. Then what happens if you tilt this roly-poly downwards? When you tilt, just take note that the pivot position changed. The pivot changes to the point of contact of the ground. So now the pivot, okay, my roly-poly will be rotating about this point. This purple dot over here. This purple dot is the point of contact, is also the pivot. Okay, so this is my pivot. Okay, my center of gravity is still at the center of this blue color part. Okay, so my center of gravity is now not directly above the pivot. Okay, it's to the left side of pivot. So this will actually create a anti-clockwise movement. So you see the line of action of the weight is to the left, or the CG is to the left of the pivot. I will have an anti-clockwise movement. So this anti-clockwise movement will cause this roly-poly to rotate anti-clockwise until it comes back to this position. The same for this. Okay, where I tilt it in this direction, my center of gravity is to my right. I will create a clockwise movement. So you need to mention about what happens to the center of gravity and what kind of movements it will create to go back to its original position. Okay, so let's take a look at a video again. Okay, so once I rotate, it's because of pivot. Okay, so after we have gone through that, you take a look at this. This is again the balancing toy. Where is the center of gravity? You should be able to identify that this ball over here and this star over here is the heavy object. It will lower the center of gravity. And in all cases, center of gravity must be in line with the pivot. So in this case, the center of gravity is directly below the pivot. So how the toy is able to remain stable? Okay, take note that in such question, it depends. Sometimes the question will ask, oh, what happens when this toy is tilted to the right? What happens when this toy is tilted to the left? And sometimes the question will be very general. How does this toy remain stable? Okay, so when it remains stable, okay, you cannot mention about, oh, it will have clockwise movements, it will have anti-clockwise movements, because I did not tell you whether I rotate this toy clockwise, to the left or to the right. So I can't tell that. So in general, we will just say it creates a moment that restore the toy, or it creates a moment that causes the toy to return back to its original position. We will just say it creates a moment. We will not state the direction, because the direction depends on how the toy is being displayed. So the first step, the center of gravity is directly below the pivot. And then how does it remain stable? Because when it is being displaced, I never tell displaced to the right or displaced to the left. I just say when it's displaced, the weight will create a moment about the pivot, and these moments will restore it back to its original position. Take note, I did not say that the CG or the weight is to the left or to the right. I did not say what type of moments it produced, because it just asked how the toy is able to remain stable. I did not ask how the toy is able to go back or remain stable when it is tilted to the right. But if the question states if it's tilted to the right, then you need to mention that the CG moved to the left, or the weight will create a clockwise or anti-clockwise movements. Okay, then you need to be very specific in your answers. Okay, so before we end off the chapter, let's do a conclusion. Some questions. For an object to be balanced, its net moments must be zero. True or false? The answer is true. Not only must its net moments be zero, its net force must also be zero in order for an object to be in equilibrium. Second question, which of the following helps to make a table lamp more stable? Okay, so if I want an object to be more stable, I'm not going to reduce the base area. I'm going to make the base heavier and wider. When I make the base heavier, I'm lowering the center of gravity. So my CG will be down, okay, and wider to increase the base area. So the answer is B. Okay, if for C, if I increase the mass of the lampshade at the top, because the lampshade is at the top, if I put more mass at top, then my CG will move up higher. The center of gravity will be higher, and this will make the lamp more unstable. Okay, so that's the end of the entire chapter.